Hello everyone and welcome to Solved, where we help you solve problems. In this video, we will be discussing which orientation of a cylinder loses heat faster due to natural convection. Is it in the horizontal or vertical orientations? With that, let's start with the problem. A 1-inch 16 BWG copper tube has its outside surface maintained at 115 degrees Celsius by condensing steam inside. A 3-meter length of this tube is to be suspended in still air at 20 degrees Celsius in an orientation that minimizes heat loss due to convection. Determine the rate of heat loss for vertical and horizontal orientations. Let's go ahead and solve that problem. Here we have an illustration of our two cylinders. One is horizontal and the other is vertical, as well as the parameters for the dimensions of the cylinder and the surface and surrounding temperatures. Now, the main difference between these two orientations of the cylinder, calculations-wise, is what characteristic length are we using for the calculations of the dimensionless numbers. For natural convection systems, we are relying on the Grashof number, Rayleigh number, and Nusselt number to get an estimate of the value of the heat transfer coefficient. Now, these three dimensionless numbers are very particular as to what characteristic length do we use in their equations. It has something to do with the orientation of the system. For horizontal systems, we use the diameter as the characteristic length such that we are solving for the Grashof, Rayleigh, and Nusselt number with subscripts of d indicating that the diameter was used as the characteristic length. This changes the equation such that for the Nusselt number, it becomes hd over k. For the Grashof number, it becomes beta g delta t d cube over nu squared. And for Rayleigh number, that is Grashof number using the diameter as the characteristic length multiplied by the Prandtl number. Now for the vertical cylinder, we simply replace the diameter with the length of the pipe, such that we now get the Grashof number with L as the subscript, that is beta g delta t L cube over nu squared. Rayleigh number with subscript of L, that is Grashof number of L multiplied by the Prandtl number. And finally, the Nusselt number for a vertical cylinder is simply HL over K. Now, this subtle difference between the diameter and the length as the characteristic length would have a drastic effects on our calculations, as we will demonstrate in our calculations. Okay? Before we proceed with the calculation of the dimensionless numbers, let's first summarize the physical properties of air at the film temperature. In our example here, the film temperature T sub F is the average between the surface temperature of the pipe and the temperature of the surrounding air. So that is 115 plus 20 all over 2. This is 135 degrees Celsius over 2. That's 67.5 degrees Celsius. Converting to Kelvin, we have 340.65 Kelvin. Now let's tabulate the physical properties of air at a film temperature of 340.65 Kelvin. First is the density. Assuming that air is an ideal gas and that we use 1 atmosphere as the pressure, the density of air is 1.036 kilograms per cubic meter. You can use the formula density is equal to PM over RT for ideal gases. Next, the viscosity of air is 2.04 times 10 raised to negative 5 Pascal seconds. Next, thermal conductivity K is equal to 0.029 watts per meter per Kelvin. And then finally, Cp or heat capacity is equal to 1003 joules per kilogram per Kelvin. Now we can proceed to solve for the dimensionless numbers important to identify the rate of heat transfer by natural convection. Those are Prandtl number, Grashof number, Rayleigh number, Nusselt number, and then from the Nusselt number, we can solve for the heat transfer coefficients, and from that, we can solve for the rate of heat transfer. We will be solving two values of each dimensionless number, one for a horizontal cylinder and one for a vertical cylinder. Okay, let's start with Prandtl number. Now, Prandtl number is the only dimensionless number in our list that will not change its value between the horizontal and the vertical cylinder because it only relies on the physical properties of the fluid itself, which is air. Okay, that is Cp 1003 times viscosity 2.04 times 10 raised to negative 5 over the thermal conductivity 0.029. Our Prandtl number is 0.706 for both systems. Okay, next is Grashof number. Remember that Grashof number is equal to beta G delta T L cube over the momentum diffusivity squared. For the horizontal cylinder, our characteristic length is the diameter, so we just have to change L with D. For beta, or the compressibility of a gas, that is simply equal to the inverse of the absolute temperature in Kelvin. That is for ideal gases, okay? Substituting, we have for beta, 1 over 340.65 multiplied by G, that's 9.81 meters per second squared, times delta T, our driving force is 115 minus 20, and then multiplied by the characteristic length, diameter in the case of horizontal cylinders, 0.0254 raised to 3. And that is divided by the momentum diffusivity, 2.04 times 10 raised to negative 5, divided by the density, 1.036, that is raised to 2. Our Grashof number for the horizontal cylinder is 115623. For the Grashof number of the vertical cylinder, we simply change the value of the characteristic length from 0.0254, which is the diameter of the cylinder. We convert this to the length of the cylinder, that is 3. Our Grashof number in comparison is very large, that is 1.91 times 10 raised to 11. Next, we have the Rayleigh number. The Rayleigh number is simply the products of the Grashof number and the Prandtl number. Let's start with the vertical cylinder. Since we now have the value of its Grashof number in our calculator, we multiply that with 0.706 to get the Rayleigh number 1.34 times 10 raised to 11. For the horizontal cylinder, that is 115623 times 0.706, we have 81,630. Now for the Nusselt number, we have two different equations for horizontal and vertical cylinders. Let's start with the horizontal cylinder. We can use this Nusselt number correlation for horizontal cylinders. You simply substitute the value of the Rayleigh number here and the Prandtl number here, execute, and then we have the Nusselt number. Substituting, our Nusselt number for the horizontal cylinder is 7.37. Now for the vertical cylinder, we are going to use a different equation. In our example here, since we are dealing with a thin cylinder, we can use the correlation Nusselt number is equal to 0.148 times the Rayleigh number raised to 0.333. This is applicable only for thin cylinders, okay? Substituting, 0.148 times 1.34 times 10 raised to 11, and that is raised to 0.333. Our Nusselt number is 751. Now that we have the Nusselt number, we can now solve for the heat transfer coefficient H. For the vertical cylinder, the Nusselt number is equal to HL over K. Solving for H, we have Nusselt number multiplied by the thermal conductivity, 0.029, divided by the length, that is 3 meters. Our heat transfer coefficient, 7.26 watts per square meter per Kelvin. For the horizontal cylinder, our Nusselt number is equal to HD over K. So solving for H, we have the Nusselt number, 7.37, multiplied by the thermal conductivity, 0.029, divided by the diameter, 0.0254. Our heat transfer coefficient, 8.41 watts per square meter per Kelvin. For the rate of heat transfer, our governing equation is Q is equal to HA delta T, wherein delta T is our driving force, and that is surface temperature minus surrounding temperature of air. For the horizontal pipe, solving for Q, we have H times area is simply the outer surface area of the cylinder, that is equal to pi d times L. That's times pi times the diameter, 0.0254, times length, 3 meters, multiplied by the driving force, that is 115 minus 20. We have 191 watts for the horizontal cylinder. For the vertical cylinder, that's 7.26 watts per square meter per Kelvin multiplied by the area of the pipe, pi dl, times the driving force, 115 minus 20. Our rate of heat transfer for the vertical pipe, 165 watts. From the results of our computations, it is apparent that the rate of heat transfer is greater for the horizontal cylinder compared to that of the vertical cylinder, although the difference is small considering that we have not accounted for radiation. Now, the results of this exercise can be interpreted in two ways. First, if we are trying to conserve the heat of the fluid flowing inside of the pipe, then we might want to go with the configuration that gives us a less rate of heat transfer. That would be the vertical cylinder. And for the opposite, if you are trying to cool the fluid inside of the tube fast, then we might want to go with a larger rate of heat transfer. That would be for the horizontal cylinder. I am inviting you to try our approach to this problem in solving a practical question. And that is, if I have a can of soda at room temperature and I want it to cool fast in the refrigerator, what orientation should I place my can? Should I place it lying down or horizontal? Or should I place it standing up or in the vertical position? You simply look for the standard sizes of soft drinks in cans and then apply the same process that we have gone through here. And let's see if you will arrive with the same conclusion that horizontal orientation gives a greater value of the rate of heat transfer. Okay? Thank you for watching, and this has been another problem solved.